Okay, so why is an impurity in a solid not necessarily a bad thing?
It allows you to have characteristics to whatever substances.
Yeah, it changes properties. Could. Why did that do that? Change, mixing those two things together could change the properties like color, if it's more or less chemically reactive, if it's going to rust easy or harder, the substance is now harder or it's softer, it's more flexible, it's less flexible. We could talk about like diamonds. If you have impurities in diamonds, usually people consider that a bad thing, but what if it makes the diamond pink? Or makes it look like an emerald or something of that nature. So it could be good because it's aesthetically pleasing. All right, so vapor pressure for ethane. So ethane is somebody have the vapor pressures of these?
Let me. So do you just like match temperature and then is that how you do it, the vapor pressures, or is there, because it's a graph now, it's like curve.
Well, it could be a curve. It just depends on, usually there's if you just Googled it, it would be, it would give you the vapor pressure at standard temperature and pressure. But did anybody find that? You found something weird?
Well, what I did is I just set them both to a certain temperature and I just gave the pressures at that temperature. Because I wasn't getting a clear answer, so I just looked up the curves and then
Okay.
Yes, and
It was dramatic though, right?
yes.
Yeah. What's the vapor pressure for the propane? Does anyone remember?
I did it opposite. I got the same pressure and was witnessed the temperature changes.
Okay.
So at 10 pressure in B, I have negative 142.9 degrees Celsius for that thing, and negative 2.3 for ethanol.
Okay. So this one's vapor pressure is going to be a lot lower. So if we're talking about Celsius temperatures, right? So vapor pressures, you had a standardized pressure, right? So I don't know what the pressure was. Let's say it was 1 atmosphere. Doesn't really matter. So you could get 1 atmosphere of pressure out of this molecule at minus 142 degrees Celsius. You can only get 1 atmosphere of pressure out of ethanol if you got all the way up to negative 2.3 degrees Celsius. So my temperature has to be dramatically higher. So why would the temperature need to be so much higher for one molecule versus another? That's going to be your answer, period. Vapor pressure is dependent upon temperature and it's dependent upon intermolecular forces. And this is dispersion, only dispersion forces. And this is a hydrogen bond because there's an oxygen hydrogen there. This still has a high vapor pressure, right? Ethanol, that's what's in hand sanitizer. That's what makes the hand sanitizer vaporize, in a minute or so after using it. But its vapor pressure is nowhere near what the vapor pressure of propane or ethane would be. So ethane is one of those 3 molecules that's going to be in natural gas or in your propane tank. So HCHHCOH HCHHH. Okay, so there's isopropyl alcohol. it's propyl because it's 3 carbons. And if you guys take 123, we'll find out prop means 3 in organic chemistry. And then it's isopropyl because the alcohol group is on the central carbon instead of on one of the end carbons. So how come this mixes with water well?
Polar.
That right there is polar. And the rest of this is small. And that's important, that the rest of the molecule is small, because if the rest of the molecule, if it was a large molecule, then it wouldn't be polar. So we put up stearic acid and I think oleic acid last class, and we were talking about melting points of those things. We were asking basically about the difference between the melting point between butter and margarine and why they were so different. And the margarine had more double bonds in it. And the end of those molecules is one of these. And a chain going off on the edge. That's very polar. But we all know that margarine and butter are not polar molecules. They have a polar portion to them, but most of the molecule is nonpolar. So it would not mix, it does not mix with water. Butter and bacon fat do not mix with water, even though there is a polar part. So this isopropyl alcohol mixes, 1, because it's got a polar section, and 2, the molecule is small. If it was larger, if this chain kept going here with more carbons and hydrogens, there'd be a point that you would reach and it would stop being polar. It would not mix with water anymore. So how do we work with these calculations?
You mean like the theory behind it, or like just the geometry style?
Yeah, first off, the geometry set. Does getting to this final equation, does that make sense mathematically? So like, what's this thing like from, I don't know, 9th grade geometry? What's this first equation? That's just Pythagorean theorem. What's the next one? Same thing. They're both Pythagorean theorem, right? But I'm looking at the triangle and looking at 2 different triangles and labeling however I want to label them. So in like, there's my hypotenuse, there's my hypotenuse. But this hypotenuse, this b squared, is also that b squared right there. It's the same thing because the triangles share a side. So I can take these a's and substitute them in for the b squared. And so that b squared becomes a squared plus a squared plus a squared, which equals 3a squared. I'm just combining like terms. And then I can get rid of the square root on the c side, the hypotenuse side, and then square root everything. And I end up with that for our cube root when I'm solving for a. So in that case, what would a be measuring? Lattice points. So then we do the X-ray crystallography on it, and then we measure the distances between the lattice points, and then we can use this equation to figure out what the radius is. So I had a couple of you just write down that whatever the lattice point distance was, it's half of that. And that's not the case. Why is half the lattice point not the radius of the cell of the atom? So this is from lattice point here to lattice point here. So A would be so why is lattice distance half of lattice distance not equal to atom radius? Because that little gap. We okay with that? I zoom in on this, maybe it'll these atoms aren't actually touching because this atom in the middle is taking up space and pushing them out away from each other. It would be half of lattice point to lattice point if we were talking about a simple cubic that doesn't have anything in the center. There's just those atoms in the corners. But we don't have a simple cubic here. We've got a body-centered cubic. So that little gap we have to take that into account. And we're taking that little gap into account with this equation right here. So you would use the lattice point distances and this equation to calculate your R. Had you look up the radius for gold? What was it? 180? 144. So no, that was the radius. The radius is equal to 144 picometers for gold. So not a super complicated equation here. If I want to know what the distance is between the lattice points, then I'm just going to rearrange this. Or actually, I'm going to leave that as is and solve for A. So A is equal to 4 times 144 picometers divided by the cube root of 3. So if I'm looking at a face center cubic for gold, this A distance right here would be 133. And then my radius distances would be 144. And so then I'd have that gap there, which is whatever 280 or 233, 333 minus 288 would be, taking into account that gap. So short explanation for X-ray diffraction. What do we got? What happens? What do you need? How about Y X-rays? The wavelength of X-rays is about the size of an atom. And I say about because there's a breadth of wavelengths associated with the X-rays, in the same way that there's a breadth of wavelengths associated with red. So red isn't just one wavelength. There's lots and lots of wavelengths that we would look at and we would call that red. Variations of red, obviously, but it's a pretty good breadth of different wavelengths. And the same situation with the X-rays. So the breadth of the X-rays gives us the full scope from the largest atom all the way down to the smallest atom. Okay, so we definitely need X-rays. And then this is an important part. What do I need besides the X-rays? What am I doing the testing on? I need to be able to whatever the substance is, I need to be able to crystallize it. That's not always easy. Sometimes crystallization is a difficult process. Like an amorphous structure, the crystallization process doesn't happen. So X-ray crystallography on glass doesn't work very well because it's not a crystal lattice structure. So I don't have any equal distance points. They're all sort of chaotically thrown in there, like somebody chucking a bunch of extension cords into a box. They're just not organized. So I need to be able to make a crystal out of it. And then I shine the X-rays through and I tune it until what happens? And the constructive interference ends up creating spots. And you can measure the distances between those spots, and that will give you your lattice structure. And so the cool thing about it is you tune it so the distance between the layers of the crystal that you're looking at you end up having exactly one extra wavelength between two layers. And so when two X-rays come in and they have an indice or they interact with one of the atoms, this one will come in and bounce, and then this one will come in and spend an entire extra wavelength. So when they come together again, this one is one wavelength back from the first one. So these guys used to be in sync up here, and when they come through, the one that it was in sync is now in front over here. But it doesn't matter because the wavelengths are the same. So they end up adding to each other regardless of the extra distance they've traveled. They've traveled the extra distance exactly like if we're thinking about cars, like one extra car length. So they're back in sync with each other. And when they go down 3 layers, they travel 2 extra distances. So they end up, or 4 extra distances. So they end up being, again, in sync with each other. We've been using X-ray crystallography for maybe 100 years now. Definitely started it early, but perfected it at least for the last 80 years. And it's definitely a tool that will continue to be used. All right, so what do we have on Rosalind? Those are the two words, two things that come to mind. She was stolen from, and she was abused, and marginalized would probably be another good one. And then over here, you'd say, not just a chemist, but also a mathematician. So when she took photo 51 and saw it, and she realized what it was she was looking at, that right there, this is the most important picture I've ever taken. And then she went and she spent an entire year doing the calculations. Literally, she finished her last calculation 365 days after she had taken the photo. And by that time, Watson and Crick had seen it because Wilkes gave it to them. And then they didn't do the math on it. They actually did something kind of ingenious, which was, we have an idea of what this should be like, and just thought up different ways that it would work. And then applied it to the image and said, okay, well, these other ones can't work because of this is what the image looks like, but this one does. And part of the reason that they did it that way is because they literally did not like her. And because she was a woman working in science at the time, that didn't help her at all. Does anybody know what else was going on at that time? This was the big thing. DNA was the big thing, to try to figure out what DNA looked like. So everybody in the world was trying to do it. And the person who was closer to doing it than them, who had an idea but had made a mistake, was Linus Pauling. We'd heard his name before. Where have we heard his name? He's the one that came up with carbon hybridization of their sp orbitals. So he's the person that said that the 2 electrons in the 2s and the 2 electrons in the 2p come down and make an sp3 hybridized orbital, so it can make 4 bonds. He won a Nobel Prize for that. He also won a Nobel Prize for years later for peace. And he's the person who came up with the numbers for the electronegativity on the table. So he was already quite famous when this was happening, and he was close to figuring it out. He had figured out something about the structure of proteins, and that was a good and bad thing for him because he was kind of stuck in an alpha helical idea when it was really a double helical idea that he hadn't seen. But if somebody had given Rosalind's picture to Linus, he would have instantaneously knew what was going on. As soon as he saw the photograph, he knew exactly what the structure was. And I mean, to this day, and Watson is 96 years old, he is still